Now that we have the language of complex numbers at our disposal, let's talk about complex vectors. So the theory of complex vectors is very similar to the theory of vectors as we know it so far, but as we'll see in a few moments, there are a few key differences. So first of all, we're going to change our notation. Instead of writing lowercase letters with arrows on top of them, we're going to start to just write bold letters to denote our vectors. And we say that this symbol, bold V, belongs to C to the n to indicate that this bold V is a list of n complex numbers. So let's look at some complex vectors. So here we have the vector -1 and then 8i plus 1. This is a list of two complex numbers. Remember that real numbers are also always complex, but the other way around isn't necessarily true. So here we have a list of two complex numbers. So this is a vector in C2. Here we have another complex vector. This vector has coordinates -5i, -15, -i minus 10. This is a list of three complex numbers. So this is a vector in C3. And here we have a vector with four coordinates, -i minus 22, 1, -1, and -i plus 2. This is a vector in C4. And here we have a vector with five coordinates, 3, 0, 0, -1, 0. This is a vector in C to the 5. Now, again, note that all of the numbers in this last vector have zero imaginary part, which is fine because real numbers are also complex numbers. So this last vector is a vector in C5. It's also a vector in R5. And one thing that we can do with complex vectors that wasn't very interesting in the theory of real vectors is we can conjugate. This is why we're adopting this new notation, because things get a little bit clumsy when we start writing bars on top of arrows. So the conjugate of a vector v1, v2 up to vn is defined with the same notation. We write a bar on top of the symbol. And what this is indicating is that we will conjugate each entry of the vector. So for example, here we're looking at the vector -3i, I minus 1, -3, I 2. So this vector has 1, 2, 3, 4, 5 entries. So we have a vector in C5, and we're writing a bar on top of the whole vector, which is indicating that we are going to conjugate each individual coordinate of this vector. The conjugate of -3i is plus 3i. The conjugate of I minus 1 is -i minus 1. The conjugate of -3 is just -3, so that coordinate doesn't change. The conjugate of I is -i, and the conjugate of 2 is equal to 2, so the last coordinate doesn't change. Now, the important tool that allowed us to do geometry in Rn was the dot product. So geometry in real space is defined by the dot product. It's a natural now to ask, well, what about complex space? So how do we do geometry in C to the n? And let's look at an example to illustrate that we might need to rethink our theory. Think about the vector I, -1. Let's take a dot product of this vector with itself. Well, we're taking the dot product of I, comma 1 with I, comma 1, which means we're going to compare the coordinates, multiply them by themselves, and add. So here we're looking at I squared plus 1 squared. Well, we know that I squared is -1, and then when we add -1 to 1, we get 0. And this is an issue, because what we're saying is that we're taking a dot product of this complex vector with itself, and we get 0, which is suggesting that this vector v is orthogonal to itself. And this feels kind of wrong, because vectors should not be orthogonal to themselves. So we have a problem here. We need an alternative to the dot product. The dot product is not going to accomplish our geometric tasks in complex space when it was perfectly fine in real space. So we need an alternative to the dot product that will work with complex vectors. So let's now define what's called the inner product. It turns out that the dot product is almost good enough to do geometry, except we have to make one subtle change. So the inner product of two complex vectors v and w is defined notationally with this angled bracket notation. We're going to take angle bracket v comma w close angle bracket, and the definition of the inner product says let's first conjugate the first entry into the inner product, and then we take a dot product of the two vectors. So let's see this with an example. Let's look at the vector v, whose coordinates are negative 3i minus 3 and negative I minus 1. And let's look at the vector w, whose coordinates are negative 4 and I plus 1. By definition, the inner product of these two vectors is obtained by first conjugating the first vector v and then taking a dot product with the second vector w. Well, when we conjugate this first vector v, we take each of the imaginary parts and negate them. So negative 3i minus 3 should become 3i minus 3, and negative I minus 1 should become I minus 1. After we take these conjugates, we now proceed to take a dot product. So now, according to the formula, we should take 3i minus 3 and multiply by negative 4. And then we take I minus 1 and multiply by I plus 1. When we do the arithmetic here, we end up with the number negative 12i plus 10. So one thing to point out about this example is after taking the inner product of these two complex vectors, we ended up with a complex number. Okay, so how does the inner product behave? So the inner product has the following properties. It is complex valued, which means that if we take the inner product of any two vectors, we always get a complex number. Remember, this doesn't exclude the possibility of our inner product being a real value, because every real number is also a complex number. This just means that sometimes we might get an output after taking an inner product that's not a real number. It's also conjugate symmetric. So remember with the dot product, it didn't matter which order we took the dot product in. For inner products, the order actually matters, but if we swapped the order, we could predict what the output would be. So the inner product of v with w, while it's not the same as the inner product of w with v, the two inner products are related by conjugation. So v inner product w is the conjugate of w inner product with v. There are also distributive and scalar laws. If we wanted to take the inner product of a scalar multiple c of a vector v with a vector w, we can factor out c from the left here, but since inner products are defined by first conjugating the first vector in the inner product, it's not c that factors out, it's its conjugate that factors out. But we don't conjugate the second entry into an inner product, so we can factor scalars out of the second entry in the inner product. V inner product with c times w is the same thing as c multiplied by the inner product of v with w. So this is almost exactly like the dot product, except in the dot product, we never have to worry about conjugation. And there are distributive laws. If we want to take the inner product of v with the sum of two vectors w and x, that's the same thing as first taking the inner product of v with w, then taking the inner product of v with x, and then adding the two results. We can also distribute from the right. If we wanted to add v to w and then take an inner product with a new vector x, that's the same thing as first taking the inner product of v with x and then taking the inner product of w with x and adding the two results. Okay, so let's see now how the inner product allows us to do geometry in complex space. Let's define a vector v whose coordinates are b1i plus a1, b2i plus a2, and then we keep going until we get to our last coordinate, bni plus an. So this is an arbitrary complex vector in Cn. Well, what happens if we take the inner product of v with itself? By definition, we're supposed to first conjugate v, so conjugate every entry inside this vector, and then we take a dot product with the vector. So now, what we're doing is we are negating every entry inside of our vector v, and then taking a dot product, or negating every imaginary part of every coordinate of v, and then taking a dot product. But another way to think of it is, if we look at the first entry of the conjugate, it's the conjugate of b1 times I plus a1. The second entry would be the conjugate of b2i plus a2. And the last entry is the conjugate of bni plus an. And when we take the dot product of this conjugate vector with the original vector, what we're doing is we're taking each coordinate and multiplying it by its own conjugate. This is exactly how we defined the absolute value squared of that entry. So what we're doing when we're taking the inner product of a vector with itself is we're summing the absolute values of each of the coordinates, but we square those absolute values. So ultimately, what we end up doing when we take absolute values and square them is we just square the real and complex parts of each one of these coordinates and then add them together. So to take an inner product of a vector with itself is to go to each complex and real part, square those terms, and then add them together, and then proceed to each subsequent coordinate. So the inner product of v with itself is the real part of the first coordinate squared plus the imaginary part of the first coordinate squared plus the real part of the second coordinate squared plus the imaginary part of the second coordinate squared, and we keep adding those squares until we get to the last coordinate of the vector. In particular, since what we're doing is we're adding a bunch of squares when we take an inner product of a vector with itself, we note that the inner product of a vector with itself is always not a negative number. So this is how we define the length or the norm of a vector in Cn. The norm of a vector in Cn is defined notationally the same way we define the norm in Rn, except now instead of using the dot product of a vector with itself, we're taking an inner product of the vector with itself. So the norm of a vector in Cn is the square root of the inner product of the vector with itself. So for example, to calculate the norm of the vector I, negative I plus 1, negative 11, and then let's maybe just go ahead and square this norm, what we're doing is we're going to each individual coordinate and then summing the squares of the real part and the imaginary part. So for the first coordinate of this vector, the real part is 0 and the imaginary part is 1. So for the first part of this calculation, we take 0 squared plus 1 squared. For the next coordinate, we're looking at negative I plus 1, which has real part 1 and imaginary part negative 1. So the next part of our calculation is 1 squared plus negative 1 squared. In the third coordinate of this vector, we're looking at the coordinate negative 11, which has real part negative 11 and imaginary part 0. So for the last part of this calculation, we take negative 11 squared and add 0 squared. When we add all these squares together, we get the number 124. So just like in the world of real vectors, we can define complex geometry using the inner product. The angle between two vectors in Cn is defined by the following formula. We take the real part of the inner product of our two complex vectors and set that equal to the product of the lengths of those two vectors multiplied by the cosine of the angle between those two vectors. This is exactly the formula we use in real geometry, except in real geometry we take the dot product of two vectors instead of the inner product, and there's no need to only look at the real part of that product. In particular, and this is the most important point we'll make here, to test whether or not two vectors are orthogonal in Cn, we don't look at the dot product of the vectors, we look at the inner product. So two vectors v and w in Cn are orthogonal if their inner product is equal to 0.